Dear student, today we are going to discuss about affine maps. Now you have studied about affine space, affine subspace, affine dependent and linear independent. Now we are going to define affine map. What is affine map? Corresponding to linear maps, we have the notions of an affine map. An affine map is defined as a map preserving affine combinations. Already you know what is affine combination. I have discussed already. Definition given two affine spaces, say E vector space and plus under the operation plus and E prime vector space and E plus prime. A function f from affine space E to affine space E prime is an affine map appendable per every family ai lambda I belong to I of weighted points in E such that summation of lambda I is equal to 1. We have f of summation lambda I ai is equal to summation lambda I f of I. That is, f is linear. In other words, f preserved by centers. You know by center already a linear combinations of points with corresponding to weighted points. Such function is called affine function. Affine map can be obtained from linear maps as follows. For simplicity of notions and notation, the same symbol addition is used for both affine space instead of using both plus and plus prime. Given any points A belong to E, any point B belong to E prime, and any linear map H from vector space E to vector space E prime, we claim that the map F from affine space E to affine E prime affine space defines such that f of A plus B, where A is a point and V is a x vector. So f of this is equal to B point and H of V. F of V corresponding to in another affine space E prime, there is H of V. Now is a affine map indeed for any family lambda I belong to I of scalars with summation lambda I is equal to 1, and any family vi vector I belong to I, since this linear combination lambda I a plus vi can be written as a, where a is constant, and summation I belong to I lambda I a bold a and a bold a plus vi, which is equal to a plus I belong to lambda I vi. This summation is can be written as, and lambda I b plus h of v vi is equal to b lambda I bold b, because in vector notation we can write as b and b plus h of vi, which is equal to b summation I lambda I h of vi. We have f summation lambda I a plus vi f of a plus I lambda I vi, which further can be written as, since f of a is equal to b, and f of summation this is equal to h of summation lambda I vi, which further can be written as b, since each is linear lambda I h of vi, where again we can write lambda I taking lambda I common b plus h of vi, which is equal to lambda I, and this is equal to f of a plus vi. This is the required relations of affine map. Note that the condition lambda I is equal to 1 v is implicitly used in Haydn call to previous lemma in deriving that lambda I a plus vi a plus lambda I vi and lambda I b plus h of vi is equal to b plus lambda h of v. This is annotations. Now we define here a concrete example. Say this is an affine example x1 x2 column vector which map this square matrix 1 2 0 1 x1 x2, and this is a translation. Yeah, and that is here we denoted that this is x by a plus x plus b. This is our translations in a2 affine Euclidean space. It is called shear followed by a translation. This is called shear and followed by uh, translations. The effect of this shear on the square, the effect of this shear on the square ABCD is shown in next figure. The use in the image of the square ABCD is the parallelogram A prime B prime C prime D prime. Let us consider one more example. The map here, dear student, you see here you see that this is a affine space E and this is E prime. When we map This A, B, C, D, these are points which make a parallelogram. When we translate it by the definitions, we get A prime, B prime, D prime, C prime, a parallelogram. It means that square is a can be mapped into parallelogram. Similarly, another example, consider this is an affine map. Since we know that this matrix 1 1 1 3 can be written as under root 2 2 under root by 2 2 by 2 minus 2 under root by 2 2 under root by 2 and 2 1 2 0 and 2 1. Now if we multiply these two matrices and by 2 under root, we get this matrix. This affine map is the composition of shear followed by a rotation. This is a shear and this is a rotations. The effect of this image on the square ABCD is shown in this figure. To find one, the image of the square ABCD is the parallelogram. If we apply image, the image of this square is a parallelogram. This lemma is important. Given in affine map f from E to E, there is a unique vector, unique linear combination linear map f vector from E vector to E vector such that f of a plus v is equal to f of a plus f vector of vi. For every a belong to E and every v belong to vector space, let E be any point. Now we prove this theorem. P be any point, we claim that the map defines such that f of v vector is equal to f of a plus v. For every v belong to E is a linear map. This is a linear map. So f from vector space E to vector space E. Indeed, we can write a plus lambda v, and this is equal to lambda a plus v plus 1 minus lambda a. Since a plus lambda v, a plus lambda a plus v plus a minus lambda bold double a, and also a plus u plus v is can be written as a plus u and a plus v. Since a plus u plus v is equal to a plus a plus u plus bold a plus v minus bold double a. Since f preserve barycenter, we get f of a plus lambda v lambda f of a plus v minus 1 over x. My 1 minus lambda divided into f of a. If we recall that x is equal to summation lambda I, ai is the barycenter of family ai lambda I, where I belong to the index family I of weighted points with summation is equal to 1. If and only bx is equal to lambda b capital I for every b belong to you, we get f of a plus lambda v lambda, taking lambda common, lambda f of a plus b 1 minus lambda f of a which is equal to lambda f of a plus b, showing that f of lambda v lambda f vector v. We also f of a plus v u plus v f of a plus u minus plus f of a plus v minus f of a, from which we get, from this relation we get f of a plus u plus v f of a plus u f of a plus v, showing that f of u plus v and f of vector u plus f of v vector component f is linear map for any other points b belong to E. Since b plus v is equal to a plus ab plus v a plus plus v minus ab plus b, which can be written as, which further implies that in vector notation f of b plus v f of b f of a plus v minus f of b f of a plus f of b plus f of b, which on simplifications gives this results. Thus f of b into f of b plus v is equal to f of a plus v, which show that the definitions of f do not depend on the choice of a belong to E. The fact that f is unique obvious. We must f of v is equal to this one. Thank you.